Okay, so let's get started. Yeah, so where are we? Right, so in this course, we talk about database, right? So in the first half of the course, we talk about how to essentially use the database systems, right? So whenever you are creating a table inside your database, what's going to happen is the database is going to create a whole bunch of files on your hard drive to store your information. Whenever you are inserting information into the relation, right, database is going to reflect that change on your hard drive. Once all the information are inside your database, you as a user could just ask a query to bring information to you. And what database is going to do is to do some magic, right? To really bring the data on your hard drive to your main memory and then to you as a user. Before Easter, we talk about how to use a database as a user, right? So the goal of the database system is really try to make sure we hide the process of bring the data from hard drive to you as much as possible, such that you as a user do not need to worry about so many complex process of how the database really bring the data to you, right? You just enjoy the functionality that you can query your data. So in the last couple of the lectures, starting I think 3 or 4 lectures ago, we start to open up this magic black box. We try to understand how does database make this happen. Now we talk about different layers of a database systems. At the top, you have a SQL query, and whenever you are giving a SQL query to a database system, you are expecting the result back. And here, if you are talking about a relational database, the result you are expecting is another relation. And then we just go bottom to the top, layer by layer. We talk about that in the last couple of lectures. So at the bottom layer, there's a disk manager. In a very traditional architecture, all of the information you have are stored on as a whole bunch of files on your file system. And the disk manager, the goal is really try to make sure that all other layers do not need to deal with the hard drive by themselves. Then we talk about the buffer manager, we talk about the access method, we talk about how to run, how to implement a whole bunch of relational algebra operators using the access method that we provide. So today is the day that we are going to put everything together. We are going to put the last bit of the missing puzzle, that is the query optimization. And we are going to put everything together and really try to understand how does the database enable such an amazing functionality. So just to refresh our memory a little bit, let's just go another path of very quick walkthrough all the way from disk manager to operator. So at the bottom, right? So what the disk manager trying to handle is all the interactions you want to do related to hard drive. How can you allocate pages? How can you delete pages? How can you fetch pages? How can you deal with locality of pages? So on and so forth. The goal of the disk manager is really try to make sure all other layers will not interact with the disk directly. And then one layer up is a buffer pool manager. Because your information actually stored on hard drive, but we want to give all other layers an illusion that the data is in memory, not on the hard drive. So what's going to happen is a buffer pool manager going to deal with operations like fetch a page, or update a page, or flash a page back to hard drive for you. And that's the interface that is provided to all the upper layers. So essentially, you are going to have a whole bunch of information on your hard drive, right? You have a smaller buffer, right? So, and each buffer contains a collection of pages, right? So, and people interact with, not people, but all the other components interact with buffer manager by just say, okay, I want some information in this yellow page, give that to me, right? So here, maybe the yellow page is already in the buffer, then buffer manager just return that to the other components, or maybe the yellow page is on hard drive. But whoever is asking the buffer manager about the yellow page doesn't need to know about that, okay? So what's going to happen is buffer manager going to maybe empty up, evict some of the pages to make some space in the buffer, bring in the right page, and then return the buffer slot to all the other components. In the eye of all the other components, it doesn't matter whether the information you're asking is on hard drive or in memory or not. Because whenever the buffer manager brings that page to you, it's always in the in-memory buffer. And then given that amazing functionality, we go one layer up. We talk about different access methods on relations. So for example, we can do sequential scan on my relation. If you have a B-tree index, I can do index scan on my relation. I can do index lookup to really access information stored on your hard drive. I could do the hash table, so on and so forth. What the interface that access method layer provide to all the upper layers is essentially a higher level of abstraction to really access information in a relational table without interacting with the buffer or the disk manager. So this is just a very simple example of a hash table that we talked about in the last lecture, right? I have my relation stored on my hard drive, right? Here I have the relation with maybe 4 tuples, right? And then I could, if you want to have a hash index on this, I could build some in-memory data structure. Here's a hash table, right? I could have a hash function and then bring in every single element to each of the bucket, right? And then within each bucket, I store a pointer to the actual data, right? So here's the record ID is the combination of the page ID and also the slot ID. Whatever I do, I give you a pointer to enable you to fetch the actual tuple if I need them. So this is just a very simple example of an index structure, right? Of course, there's a whole bunch of fundamental questions we need to understand and how to design the hash function, how to deal with collisions, so on and so forth. We talked about a whole bunch of strategies in the last week. Once you have all those methods, right, we can go even one layer up. And then last week, we talked about a whole bunch of implementation of different relation algebra operators. For example, join, for example, projection, for example, selection, so on and so forth. So that is what happened in this layer. The interface we are giving to the query optimizer is even a higher level of abstraction to access information. Instead of saying that, okay, I want to access information using B-tree, no, you just say, okay, I want to do the following relational algebra operator. I want to join R1 with R2. If that is what you are telling the operator execution layer, it's going to actually automatically run that for you by picking the best access method. You do not need to deal with the access method layer. So this is actually where we are. Today, we are going to talk about, oh, sorry, yeah, so here's another slide, right? So this is actually a whole bunch of different ways you can implement the same relation algebra operator, right? For example, if you want to join between R and S, we talk about a whole bunch of different ways you can do this. You can do nested join, you can do salt-merge join, so on and so forth. For each one of them, we could support different join predicates, right? And also last week, we talked about essentially a cost model for each of these. So today we are going to put everything together. Okay, we are going to talk about really the top layer of a database system, that is the query optimizer. So essentially, given a SQL query, we want to generate a good execution plan. And here by execution plan, it is essentially a DAG or a tree of relational algebra operators, okay, such that we can actually use the operator execution layer to really answer the query provided by the user. So what do we need from the lower layer, right? So essentially, we are going to have a physical plan, an execution plan, with a whole bunch of relational operators. We are going to call the operator execution layer in the right schedule to actually run the query for the user. So this is the first thing we are going to talk about today, and then we are going to talk a little bit about tuning. So here's the process that's going to happen in this layer. User give me a SQL query, and then I'm going to have a parser inside my database to really translate what the user gave me into something that my database system can understand. We call that the logical plan. Why is logical? Because it is what the user logically wants. So given the logical plan, I still don't know how to run it, but this is a very precise definition about what the user is asking me to do. You can think about that as one relational algebra expression or relational calculus queries, depending on how you store it inside database, it doesn't matter, okay? And then what's going to happen in the query optimization layer is I'm going to translate that into a physical plan. And that is something the database system can just take it and run and get the result back to the user. If you compare the logical plan and the physical plan, there are a lot of really important differences. So at the first glance, the physical plan, let's look at another relational algebra kind of expressions. But however, for each of the operators in the physical plan, I also need to tell you, okay, I'm going to run this operator using this algorithm, right? For example, I'm going to run this join operator using Grace hash join. I could run this operator using sort merge join, right? Whenever I'm accessing information, I do one selection, I'm going to use B plus tree, so on and so forth. You have all those annotations about how database is going to run each of this operator. And also I can play with the join order, right? For example, you have three relations. I could join the first two relations first, and then I join with the last one, or I could do the other way around. So I play with join order, and for each operator, I tell database, okay, this is how you are going to run it. So this is a physical plan. It is a well-defined abstraction such that the database can just take a physical plan and run it, okay? So this process that translating a logical plan, which is just a very simple correspondence with what the user is actually asking, to a physical plan that database can actually take and run, is the job of a query optimizer. And once you have the physical plan, right, then it becomes simpler because every single operator, we already know how to run it using the operator execution layer that we talked about last week. So if you want to build such a functionality, right, to really come up with a physical plan, giving a logical plan, there are two fundamental questions that we need to understand. The first fundamental question is essentially how to run a physical plan, right? You give me a physical plan. What is my implementation about running that? How can I put all those operators together, right? So as we will see, there are many different ways you can do it, and we are going to focus on one of the simpler ones. The second fundamental question is, given the same logical plan, there are so many different physical plans that I could use. How can I pick the best one to use automatically for the user? This is essentially the two fundamental questions that we need to understand if we want to build a query optimizer. And we can unpack it a little bit. So there are actually four smaller questions that we are going to look at one by one. So there are so many different details about query optimization. It's a research that people have been doing over the last half a century, right? So since 1970, people start to do this. We're going to see an example later in the course. So, but essentially, there are only four kind of fundamental questions that you need to think about, and the answer might be non-trivial, but the question to think about is relatively well defined. The first question is the execution model. When we say we have a tree of operators, and each one of them has an annotation about which access method, which operator execution plan I'm going to use, right? So what do you mean by putting those operators together into a tree? And if you give me a physical plan, how can I run it, right? So that is execution model. And given the execution model, the second question we need to understand is the cost model, right? Because there are so many different physical plans that I can use for the same logical plan. I need to be able to essentially estimate the performance of speed or I/O, whatever performance metric you want to use. I want to estimate the cost of the physical plan without actually running it, because then I can actually pick the physical plan with the smallest cost. Okay, so there's a cost model. And of course, there's a relationship between cost model and execution model. For different ways you are running all those physical plans, there are different cost models, right? And then the third question is the search space, right? Because given the logical plan, I want to find the best physical plan over a set of potentially possible physical plans, right? So how can I construct that search space, right? So that's another question. And then the first question is the search algorithm, right? So now I have the search space. I have a whole bunch of physical plans that I could pick for your logical plan. And for each of the physical plan, I know my estimated cost. How can I search it? how can I really find the physical plan to use? Because the search space could be extremely large. I need to do something smarter than just enumerate all the physical plan and pick the best one. So these 4 questions are relatively well defined, but the answer to each question is not trivial. And we are only going to kind of scratch the surface today. But the set of questions to consider when you are building a query optimizer is relatively well defined. So let's look at this one by one, and then you will know how to build a very simple baseline, traditional, right, whatever, like query optimizer. Okay, so execution model. What do we mean by this? What we mean by this is giving a physical plan. Okay, so it's a relational algebra expression, right? And for each single operator, I have some annotation about how to run it. What is the process of actually running this, right? So what do we mean by each operator? What abstraction should we provide? So there are different ways to put all those relational algebra expression together. So there's the iterator model that we're going to talk about. There's a materialization model, and there are other models about how you run it. So the simplest thing is called the iterator model, which has a very simple view. We actually think about each node in the physical plan corresponding to one operator, right, as an iterator. It takes as input the output of a whole bunch of other operators, and each one of them is a stream of tuples. Okay, and then the interface provided to all other operators is also a stream of tuples. And whenever I want a tuple from this operator, I just call a function called next, which gives me the next tuple in this stream of tuples. So it is very simple, right? So once you take this view, you have a tree of iterator, and then you have a leaf, and you have a root node of the tree. To get an answer of this query of like corresponding to this physical plan, you just call the next function of the root operator, which is going to give you one tuple. And then what's going to happen is that the root operator going to call the next function of all its children operators, which is going to call the next function, call the next function of their own children. So that is one view about how to run a physical plan. So if you think about this, right, so you are going to call the root again. So there's corresponding to one execution model called volcano model, right? So why? Because if you think about this, right, so to get a tuple from the root, I call the next, they call the children, then I call the next function of the grandchildren, so on and so forth. Each of them are going to bring the data from the bottom to the top. So it's like a volcano. All the data are going to flow from the bottom layer all the way up to the root layer. So now let's look at one example, right? So here I have a very simple physical plan, right? So I say, okay, so this is my query. I want to do essentially a next loop join between R and S. I want to do sequential scan on R, I want to do sequential scan on S. Together, I have the next loop join here. And then I'm going to join the result of RS join, of R join S with T, okay? Also using next loop join. So how can I run this plan? So essentially you are going to call the next function of the root. You say, okay, give me the next tuple that you have. And then next loop join is going to do the following, right? It's going to call the next function of the last child to get one tuple, right? Which is going to call the next function of the scan tuple, of the scan operator over R, right? So, and then you reach the bottom, right? So, and then this operator is going to bring one tuple in the string to you, going, for example, R1. Because I'm doing next loop join, right? So the second next loop join operator is then going to sequential scan S, right? So how can I do it? I just keep calling the next function of the scan operator on my right-hand side, which will give me the next tuple in the string. For example, S1. I bring that back to my operator. Maybe I check whether it's a match or not. and then continue to do the scan. I call the next function of my right scan operator, give me another tuple S2, right? So hypothetically, we say, now we find a match, right? So then the next loop join operator going to return this pair R1 and S2 back to its parent, because the parent is still waiting my result for its invocation of my next function, right? So I bring this R1 S2 back to my parent, right? Which then start to sequential scan the relation T, right? So in this case, I'm going to call the next function of relation T, right? Bring back, for example, T1. I check whether it's a match. If there's a match, okay, great. I have R1 S2 T1 as one tuple in my result. Then I return to whatever application that's calling the next function of the root. So I keep doing this, right? So, and then I get the result. So this is one potential way that you can actually run a physical plan by just treating each operator in the tree as an iterator, which only give you a very simple abstraction. That is, I have a next function. You can get the next tuple from my string of tuples, right? To implement this, I can call the next function of all my children, right? Which will give me the next tuple of their specific, their corresponding string of tuples. So, but there are pros and cons, right? In like when we use iterator model like this. So the good thing about this is really provide a very generic interface for all operators, right? So it's really good at hiding all those implementation details for all those operator execution methods we talked about last week. Right? It doesn't matter whether you are doing next loop join, doesn't matter you are doing sort merge join, right? All of them can be modeled using this very generic interface. That's a good thing. And also it's very easy to implement, right? It's very clear what to do in any phase, right? So it's relatively memory efficient because each operator do not need to store a huge amount of result such that it can return back to the parent, right? It only need to calculate the one tuple and then it can return. So it could be memory efficient, right? So you can support some optimization technique like pipelining, right? So it's very easy to support parallelization and distribution, right? So, but there are also bad things about iterator model. For example, there are going to be really a lot of function calls, right? So whenever I want to get one tuple from you, I need to do one function call, and in turn, you are going to do a whole many other function calls, right? If my result contains millions of tuples, then you have at least millions of function calls, maybe even more, right? So it could be introduced kind of high overhead of function calls. That could be one potential disadvantage. And second is if you look at instruction cache locality, right? So this might not be the best approach that you could have, right? So this is kind of the pros and cons of iterator model, but there are other ways for you to run it. For example, another way is called materialization model, which take another extreme. Instead of asking my children to give me the next tuple, I'm going to ask them to give me the whole relation. I mean, I'm going to ask you to give me essentially the result you have, right? So here, if you take this view, each node in the physical plan becomes the following thing. It's provided to all the other operator a materialized relation, right? That's my result. And then it's going to take as input the result, which is relation from all its child. So you can actually do this, right? Each operator processes input all at once, and then give back the output all at once, right? So just take this example, right? So what could happen is the next loop join operator going to have one result, just give the whole relation back to the parent, right? And then the root node going to produce one relation and give back to the application. And that could be another view about how to run a physical plan. So when does this make sense, right? So this type of execution is good when your intermediate result is not too much larger than the final result, right? So in that case, I'm not wasting a whole bunch of space. However, if you think about this, you might want to have, like assuming you have the cross product between two relations followed by selection, right? In this case, the result set of the cross product could be so much larger than my output. In this case, just materializing the result of the cross product could be very, very slow, right? So this is kind of the trade-off, right? If the output of all the operators in your physical plan is not so much larger than the final output, then this way of doing things actually makes sense, right? So if you do those like transactional queries or LTP, right? I mean, often it makes sense, right? But if you are really trying to do those analytical queries, sometimes that can cause problem. So there are actually things in the middle, right? We talk about the iterator model, which think about each operator providing a stream of tuples, and I can only get the next tuple. We talk about the materialization model, where every single operator gives you all the results back. But there's something in the middle, right? So there's something called a vectorization model, right? Where instead of giving back the next tuple, it's going to give you back the next batch of tuples, right? You can think about this as the kind of compromise between the iterator model and the materialization model. Okay, I give you more than one tuple, but also I do not want to give you the whole relation back, right? So it's kind of good for many things. For example, if you have analytical queries, this is often very efficient. And because I'm returning a whole bunch of tuples, I could use some additional optimizations provided by the hardware. For example, I can do SIMD, right? I can do all those AVX instructions to really process those batch of tuples more efficiently. This is just 3 examples, like about how you can have different execution models for the same physical plan. So once we decide on the execution model, so now let's talk about the second question. That is, given a logical plan, right? So how can I define my search space, right? So essentially, if you give me a logical plan, right, I can actually generate a whole bunch of physical plans by playing with different things. I can play with the join order, right? Your logical plan has R join S join T, right? I could do S join T join R, right? So I could join the relations different order, right? I could rearrange when does each operator happen, right? For example, in your logical plan, you could have I first do the join, then do the selection, but I could push the selection down, right? I could do the selection first, then do the join, right? So there are so many different ways you can generate semantically equivalent physical plans given the same logical plan. So how can we think about this, right? So there are, again, so many different ways that you can think about how to generate search space. And here we talk about one specific way of doing that. That is by defining a set of transformations, and we call them query rewriting rule, that will take as input a query plan and output an equivalent query plan. So once we have all those transformations of plans, right? So we can actually generate a search space by just applying them again, and again, right? So what is a query rewriting rule? What do we mean by equivalent? We can define it in a very precise way, right? So the input to a transformation is a relation algebra expression E, and output of a transformation is another relational algebra expression E prime. So when we say they're equivalent, we mean that for all possible database instances I, these two expressions going to give you the same answer. So now let's talk about a little bit of this, right? So let's define this set of transformations. So one transformation that we could potentially have is conjunctive selection operators can be deconstructed into a sequence of individual selections. For example, if you give me in your logical plan a selection operator and have two predicates, sigma 1 and sigma 2, and then I do selection on E, you could translate that into a different plan that you have two selection operators. You first do a selection of sigma of theta 1, and then you do selection of theta 2, and then you do E, right? So this is just one example of a very simple transformation you can apply to your logical plan to get another plan have equivalent semantics. How to prove it? It's actually very easy to prove, right? So you go back to the definition, right? The left-hand side have this semantic, the right-hand side have this semantic. It's very easy to prove, right? Just go back to definition, right? So why are they equivalent? So we are not going to do this type of proof for all the other rules that we are going to talk about. But one thing to really keep in mind is do not take those rules for granted, right? For every single rule that we are going to talk about, underneath the cover, there is a formal proof. We are not going to talk about those proofs because in many cases, they are not that interesting, but there is a proof, right? So do not take this kind of for granted. So essentially, like visually what's going to happen is, assuming your plan, you have one operator deal with selection of two predicates, right? So this rule going to translate that into a different plan that you have one selection operator over theta, over theta 1, and you have another selection operator over theta 2. So here's another rule, right? So selection operators are commutative, right? So what do you mean? You have selection of 2, I could do selection of theta 2 and selection of theta 1. I can just change the order. It doesn't make any difference, right? So this is just another local transformation of your plan, right? If you have a plan, look like the left-hand side, right? You have theta 1 for the theta 2. I can apply this rule to translate that into something semantically equivalent. And there are more rules we can apply, right? For example, if you have the projection operator, right? So essentially only the last projection is needed, right? So I have projection kind of over E to project that to a set of attributes T2, and then I do another projection to project that to T1, right? I don't need to do T2. I can just get rid of it, right? So this is just kind of virtually what's going to happen, right? So you have T1 followed by, so you have T2 followed by T1, right? I can just get rid of T2. It doesn't really matter for projection. So yeah, another transformation. It gets more interesting, right? For example, if I have a selection followed by cross product, then that's become a join, right? Which is very natural, right? So that's almost a definition about what a join is. So you can make that a little bit more interesting if I have theta 1 as a selection followed by a join with condition theta 2, right? So I can also combine them together, right? So this one is the same as doing the join on the predicate theta 1 and theta 2. So again, right, so I can change my join order, right? If I have E1 join E2, right? So that's the same as E2 join E1, right? So what's going to happen is if you have a join tree look like this, I join the left-hand side with the result of the join of like using theta 2, right? So I could change the order. I could put this child to the left and then put this child to the right, right? So I can do this type of local transformation for my plan. So natural join is associative, right? So in the sense that if I have a join tree that I join, I don't know the color it is, like green and the purple together first, then join with the orange, right? I could change the order to say, okay, let me join with the orange, with the green, then join with purple, right? So in this case, if the result set of this operator is smaller than this, then you have a win, right? So, but these are semantically equivalent. It's kind of very easy to prove. And you could do something called push down selection. Essentially, whenever you have a selection over a join, and assuming your selection predicate only involve one relation, right? So you could push it down, right? So essentially, you could say, I have my selection over join, right? So I could say, this predicate theta only involve the left relation. Then I could translate this plan into something look like this. I can have the join over a relation after selection, right? I could do the selection first. If I'm able to do it on a single relation, then I join with other relation by just looking at the result of the selection. Okay, I could do that. So this is a very popular optimization that database is going to do automatically for you, right? So the intuition is, since you are doing the selection first, right? So the result of the selection hopefully will be much smaller than the actual relation, right? So then I get a win. Then I do not need to look at too many tuples for join, right? So you could do a whole bunch of things, right? So this is actually another plan where you have a kind of projection to L1 union L2 over a join, right? You can also push down kind of the projection, right? And then I do not need to look at all the columns, right? So I only need to look at the column that makes sense before you do the join, right? So another potential rule, right? So is you can change the order. We don't have union, we don't have intersection, right? So that's very natural, right? You can actually have all those associative rule for union, for intersection, by just changing the order, right? So you can have different rules like the selection operator distribute over union, intersection, right? So on and so forth, right? When you have a selection over a union, right? So I could do the selection first, then I do the union, right? And then when I do the union operator, I'm dealing with fewer amount of tuples, right? So all of the rules you could apply to really translate one plan into a semantically equivalent plan, right? So there's a whole bunch of this, which actually makes sense. So given all those rules, right? So you can start to generate kind of an alternative plan given your input plan. For example, if I have a kind of a query, sorry, you have a query look like this, right? So I have three relations. I have a branch of a bank. I have the account of a customer, and someone deposited money, right? So I want to find the name of all the customers, the account at a certain branch, and the account balance over 1,000, right? So you could have a logical plan that look like this, right? You do one projection, then you do a like selection or the join, right? And then you can actually apply each of the transformations, right? You can change the join order, right? So instead of join account with depositor, right? So I join branch and account together first, right? And then I push down my selection, right? I only look at the branch table with this branch. I look at the account with this balance, and then I do the join, right? So then you get the final one. So each one of this, like four of this, they are semantically equivalent. They are actually giving you exactly the same thing for all possible database instances. However, they have different cost, as we will see. Okay. So this is just like kind of a visualization of this, right? So your input could be a plan tree on the left-hand side. By applying all those transformations, you can bring them to a plan look like the right-hand side, right? So this defines the search space, right? Whenever I'm searching a physical plan, I need to make sure they are semantically equivalent to your input. There are so many different ways you can construct a search space, but one way to construct that is by treating the search space as a result of applying a whole bunch of semantically equivalent transformation over your input. So the third question that we want to understand, not what do we know? We know what do we mean by running a physical plan, right? We talk about the execution model. We talk about the search space, right? So what are the possible set of plans that I can look at to pick? And then let's talk about the cost model. The cost model essentially, you have a physical plan in my search space, and I know it is semantically equivalent to my input. I want to estimate how fast it is because I want to pick the physical plan that is fastest, right? But I do not want to run them to know the answer because once I run any of those, I get the result, right? I don't need to try another one anymore. I cannot run my physical plan over my data, but I need to estimate it in order to pick the best one. So the role of the cost model is really try to estimate the performance of a given physical plan without actually running it. So there are two questions that we need to understand if you want to build a cost model. The first one is how can we estimate the performance of each of these operators? And second is how can we combine multiple of those operators together to have the final cost of this whole plan? So the second question is actually easier, right? Because if you know the cost of each operator, right, you can actually consider it together with your execution model. You will find some way to put them together. So in today's lecture, we are going to focus more on the first question. That is, if you give me one operator, you tell me how to run it, you tell me the access method you are going to use, how can we estimate the performance of that operator? Last week, whenever we are talking about the execution model, or like the implementation of each operator, right? For example, the selection operator, we talk about different ways you can do it. You can do heap file. Here's the IO model. You can do the uncluttered B tree. Here's the IO model. You can do clustered B tree. Here's the IO model. You can think about each of this IO model as a simplified version of this cost model, right? So there are a lot of constants here, right? For example, how many pages you have in relation, how many tuples you have in the relation, how many tuples you have in the result, right? So on and so forth. I can just plug in all those constants into my IO model and I know the cost. So what's hard about this? The difficult thing is actually the term that I highlighted, the alpha CR. And as you remember, this is something we call selectivity. Essentially, given an operator, I want to estimate how many tuples will I have in my result, right? So because if I do not know about this, I have no idea about how fast this operator is going to run. And also, if you have a parent operator using my result, I need to tell you how many tuples you are expecting, right? So it turns out whenever you are building a cost model, the fundamentally hard component is actually how to estimate the selectivity. And that is something we are going to talk about. So there are other constants in the cost model. For example, how expensive is the read IO, how expensive is the write IO, right? How many tuples you have in your relation, so on and so forth. So all those constants are relatively easy to be measured, and then you can just put them into the cost model, then you are done. So if you look at all the cost model, the only term we don't know how to estimate is actually the selectivity, right? So that is something we are going to focus on. In database, that's a problem that we call cardinality estimation, okay? So what is this problem? Essentially, we want to know how many tuples a query would return, and we are going to decompose it to another question that we want to understand how many tuples each operator going to return. So this is the core of query optimization. It's not a solved problem at all, right? You can see there's a paper a couple of years ago to really talk about the whole landscape. So here we are only talk about the basics about query optimization. So essentially, what's the problem? The problem is as follows. I have a relation on the left-hand side. For example, I have a whole bunch of person, I have ID, I have age, I have name. I have one operator. For example, I want to select how many, I want to select like all the people have age equals to 5. The goal is I want to summarize my relation into some data structure, hopefully smaller than my original relation, such that I can take that summarization and take your query and estimate how many people will have age equals to 5 without actually running this query. So there are many different ways you can construct that data structure. For example, you can do subsample, right? And I can subsample 10% of my data. And whenever you want me to estimate as like cardinality, I run this query on this smaller subsample data set, and then I extrapolate from that, right? So that's one way to do it. So today we are going to talk about something even simpler than that, and that is called histogram. So now let's take a break, and when we get back, we will continue to talk about histogram, right? In the meantime, if you have any questions, yeah, I'm here to answer them. Okay, so let's continue. So we were talking about the problem of cardinality estimation, right? So I have my relation, you give me one operator, and I tell you essentially how many tuples I'm expecting this operator to return. That sounds like a very simple problem, right? So the game that we are trying to play is we want to summarize each of the relation into some smaller kind of data structure such that I can actually estimate the cardinality without running the real thing, right? So one simple way of doing that is something called a histogram, right? For example, you have a whole bunch of discrete values in your relation, right? So you could build a histogram that looks like this, right? Your x-axis is all the possible values that you could take in your data, and the y-axis is the frequency, right? So how often does each value appear, or how many times each value can appear, right? So in this case, if you have a, for example, the age kind of attribute, assuming is discrete, assume that, right? So and then you can just say, you want to see the selection operator, right? 8 equals to 5. Then I just take one bin in this histogram that return that to you, right? So that's a very simple way for you to do cardinality estimation for discrete value, right? And assuming your domain size is not that large, right? So it is not that easy, right? So I mean, here I only cares about selection operator with like over a single attribute is kind of easy, right? But the challenge is, for example, look at this operator, right? So I have a selection operator over 2 attributes. I want to get essentially an estimation about how many tuples that you have here. Age equals to 2 and has postcode equals to 8006, for example. So assuming you have 2 histograms, one for each attribute, right? So I could have one histogram about the age, I could have another histogram about the postcode. But this doesn't give me a good estimation because there could be correlation between age and the postcode, right? For example, maybe all the young people happens to be some postcode, right? So then, then I don't really know how to combine these 2 histograms into my estimation. That's actually the hard part, right? So there are so many different ways that you can do. You can actually learn the correlation. You can pre-compute some of the higher order statistics, right? So, but the baseline is, let's assume these 2 attributes are independent, right? So if you make that assumption, I'm making clear, right? This is assumption that could be wrong, right? But if you're making that assumption, you can actually use these 2 smaller histogram to do cardinality estimation, right? By just combine them together, right? You kind of multiply how many people have age equals 2, how many people have postcode equals to 8006, right? Put them together, divided by the total, you are done, right? So it's easy to see that in many cases, this may not give you an accurate answer, right? Because we are making an assumption that is actually very, very strong. So in practice, right, people have a whole many different ways to improve over this baseline assumption. And that is why cardinality estimation is a kind of research area. People have been doing this for 50 years and continue to do so. So for continuous value, right, so you can also do similar things like a histogram, right? You can kind of put all those values into different bins, right? For each bin that you have the frequency, right? So, and if I'm asking you, say, so give me all the people with age between 25 to 45, right? So you can make some assumption, for example, values are uniformly distributed within each bin, right? Then you can give me one estimation. If you really cares about correlation, right? So you could build some higher order histogram, right? For example, like if I only care about 2 directions, right? So my histogram has 2 dimensions, right? So for each combination of the values, I have a bin, right? So then I have a histogram, and you could do that. So the challenge here is that I cannot build this type of thing for all the combination of attributes. It's way too expensive, right? So something that you could do, not you, but database system could do, is really try to pre-compute how strong the correlation is between different pairs of attributes, and only do this for those highly correlated pair of attributes, right? So that could be like another thing database can do. So we are not going to go really deep about kinetic estimation, and we can take the whole course about kinetic estimation and probably will not also finish. So one thing that I want to comment on is many of you guys are taking the machine learning course, and many of you guys are going to take it next year, right? Depending on which semester you are in. So kinetic estimation is actually one of the database problems that could really naturally benefit from machine learning. Because if you think about fundamentally, what are the problems we are trying to solve? Is we have a high dimensional joint distribution over my data, right? Each attribute in my relation is one dimension in the space, and every single row is one point in a high dimensional space, and a whole bunch of samples over that. I have a really large high dimensional joint distribution, right? And I want to approximate it using a smaller data structure. Right? I want to automatically have a kind of compact way to capture the correlation in the high dimensional space. And if you are taking the machine learning course, or if you are taking that later, right? So you can see the connection is actually very, very clear. So that is why actually people keep applying machine learning to systems. Right? Kinetic estimation is actually one of the early problems people play with how to use machine learning to really automatically learn the joint distribution, right? And it's a very kind of hot topic today, kind of in database system research. Okay, so we talk about three things, right? We talk about the cost model, we talk about search space, we talk about the execution model. So essentially, we kind of given a logical plan, what do we know? We know how to generate a set of semantic equivalent physical plans. We know the search space. For each physical plan, we know an estimation of the cost. Now let's put this together and talk about how to search within that search space to get a physical plan with the largest cost. With the smallest cost. So how to search? So why is this like a question that is hard, right? So if you give me a like SQL query, like I want to join R with S, right? So there are not that many things to search for, right? So I have 2 join orders, I have maybe 10 different access methods. I just try all of them, right? They are done, and you could do that. So the problem here is real world applications are very complex, and the SQL query you are going to write in practice is way larger than all the SQL query you have been looking at in this course. So this is just a very small query in TVCDS, right? So, and you can see it's already pretty complex, right? So, and usually people could join kind of relations, like have a join query over maybe 10 or 20 different relations, right? So the complexity of the search space is grow really, really fast. So this is just one example, right, about how hard the problem is. Assuming I have n different relations, R1 to Rn, and I just do a very simple query, just do natural join. And assuming I have a single rewriting rule that join are associative, right? So you have E1, E2, E3. I could join E1, E2 first and join with E3. I could join E2, E3 first and join with E1, right? Assuming you have this very simple rewriting rule, how many plans that I need to look at, right? So as you can see, there's a whole bunch of them, right? The search space is extremely large, even if you have only one transformation. And we talk about 12 of them, right? And real world queries are even more complex than this very simple example. So we need to do something, right? To really have a practical search process in that very complex search space. So there are different ways to look at this. So like first one is clear, we need to do some compromise, right? Otherwise we cannot make progress, right? Yeah, so we have a question, go ahead. So someone raised hand, right? So do you have a question? You have a question, just unmute yourself and speak up.
Was just an accident, sorry.
Okay, sure. Okay, so yeah, we need to make some compromise, right? Because we are talking about an exponential large search space. We need to do something. One way to compromise is to constrain the search space. And one example system of doing that is actually the first relational database system called SystemR, developed by IBM back to the 70s. Right? So their view is, okay, so instead of considering all the possible join order, let me only consider the left deep join tree, right? Which is actually in the middle, right? So I always join two relations, and then I join that with another relation, join that with another relation, right? So you always grow the join tree by making the left-hand side deeper and deeper. So I only consider that. The rationale is left deep join tree actually allow you to generate all the fully pipeline plans, in the sense that I do not need to keep the intermediate result of my intermediate join operator. Right? I can just fully pipeline the whole thing. Right? So that's the rationale. So this actually brings the complexity down, right? So which is still exponential, but actually much, much faster than just exploring the whole search space. So given this compromise, right, so you can define the following search process, right? So I want to enumerate all the possible join orders that give me a left deep tree, right? So, and then for each join order, for each left deep tree, I enumerate different plans for different operator. Right? I try hash join, I try salt merge join, I try nest loop join, right? And for each of the operator, I also try different access method. Maybe I should do B tree, right? Then I have, for example, index nest loop join. Maybe I should use sequential scan, then I have nest loop join, right? So you try all combinations, and you could do that using dynamic programming, right? You could get the optimal plan of when you have a single relation, right? And then you can continue to grow it, right? And then you can have the best two relation plan. You can find the ways to join a relation with the best one relation plan, so on and so forth. We are not going to go deep into the dynamic programming algorithm because that is really complex. So there's a one section in the book, right, that you can actually read it. So it's still very slow, but it's kind of faster than enumerating all possible join trees. And there are different ways that you can make compromise, right? So another way of doing this is by just do some heuristic-based optimization. And one example system of doing this is a system called Spark SQL, right? So many of you know Spark, right? So this is just a SQL engine built over Spark, right? So at least a couple of years ago, when they first have it, they actually have a heuristic-based query optimizer, which is actually very interesting. So the intuition is cost-based query optimization is very expensive. Even with the dynamic programming thing, even if you constrain the search space, often it's very slow. So then essentially we try to use heuristics to reduce the number of choices that we need to make decision in a cost-based fashion. So essentially it's try to apply transformations without thinking about the cost. For example, I always, you give me a logical plan, I always push on selection. Okay, I don't care whether it helped me or not in your cost model. I always push on selection. I always push on projection, right? Whenever you have a multiple relation to join together, I always join the one, give me the smallest result set, right? So I have a whole bunch of heuristics that you can apply to translate, to transform your input logical plan into a physical plan. And that is my query optimizer. Okay, so some systems only have heuristics. Some systems just apply those rules and just run it. Okay? Some systems will actually combine the heuristics with kind of a partial cost-based optimization, right? If you look at those like real-world data system, like SQL Server and the one provided, or other things provided by Oracle, right? So and often it's a hybrid thing. You have a whole bunch of heuristics to apply transformation that should work in most of the cases, and then you filter constrain your search space and do a partial cost-based optimization. So this is just one example, right? For example, one thing I can do is I have a logical plan. I always apply this. I always decompose your complex predicate of selection into multiple smaller ones, right? And then I just push down them as much as I can, right? So, and then I just play with the join order, right? To do the join that has smallest like result set first, and then I get one query optimizer based on heuristics, right? So potentially this is another thing that you could do, right? So you can add other heuristics. For example, I only prefer algorithm that I can fully pipeline in, right? So on and so forth, right? You could just apply those heuristics and do query optimization. So now we walk through these 4 questions one by one, right? Now we have a really basic understanding about how to build a query optimizer. You have execution model, you have a cost model, you have search space, and you have some heuristic you are going to do to really efficiently search within that search space to minimize your cost. Okay, so that is what we have about database systems, right? We actually talk about each of these layers. So now let's look at one demonstration about what database is trying to do. Let's copy this. Okay, so everyone knows we have the Katacoda thing, right? So one thing that I really want to emphasize is we really want you to play with database by yourself. It's very important. If we are learning a programming language, essentially, right? So there's no way I can teach you without you actually doing the practice, right? I hope I can just give a lecture, you magically know SQL, but that won't happen, right? So we have the Katacoda thing, which is a very easy way for you to play with database without all those installations, right? So there's actually, like here. So this is the Katacoda for the second hands-on session, and we are actually going to use it in our example. So whenever you are using database, right? Whenever you are, let's try to install this relation. Yeah, so whenever you are writing a SQL query, right? So in PostgreSQL, there's one special keyword called explain, right? If you have the like if you have this before your query, it's actually going to show you the final physical plan that database plan to use, like for this query. Okay, so and this might take some time to actually calculate all the examples, but you can actually copy the result of the expand query, right, to some other tool and actually show you something much more beautiful than what you get in PostgreSQL, right? So this is just one kind of like one physical plan for this query. Okay, I'm drawing these 3 relations, right? So as you can see, first one is a tree, right? So and then for each of this operator, for example, there's one operator called sequential scan. There's a one operator called the hash join, right? And if you open the hash join or like operator, there's a whole bunch of statistics, right? So there's the estimation of the startup cost, right? So and there's a like estimation of the total cost. So this is how many rows I'm going to provide. This is how wide each row is, right? So if you multiply them together, you kind of know how large, like for example, in megabytes, right? So my result is for each of this operator, you can see, right? So for example, we can do sequential scan, right? So here you say, the total cost of this one estimation is this, right? So this is the number of rows I have. This is how wide each row is, right? So yeah, so essentially this is actually one example of a physical plan that you can get if you run explain, right? So and then the database is going to run this for you, going to sequential scan, go to this, go to hash join, and so on and so forth, right? So this is one example of the query plan you can see inside database. So in practice, inside PostgreSQL, right? So yeah, a little bit slow. Inside PostgreSQL, when you run this query, right, it's going to actually give you something like this. As you can see, it's just a kind of another representation of the plot, right? So how to read it, right? So you first look at this. It's going to do sequential scan on artist, and then it's going to do hash, and then do a hash join together with artist, and release by, and so on and so forth. For each of the node, you can see this is my estimation of the cost. This is my estimation about how many rows it's going to return. This is how wide each row is, right? So as you can see, right, so all the things we have been talking about today, right, they come together inside the database system. So in practice, right, performance is a complex process, right? So you need to consider so many different things. So in the course, we say, we just count I/O, but in practice, the read I/O and the write I/O, they are different. Sequential I/O, random I/O, they're also different, right? So you can do optimization like in so many different kinds, right? So, and here we talk about single query. In practice, we have multiple queries, you can do multi-query optimization, so on and so forth. Right? So this is what a large portion of the database community was doing in the last half a century, right? So, and it's a very interesting research topic even today, right? So this is about database systems. So now let's talk about another thing that's called tuning, right? So whenever we are talking about database, right? So we always give you a very clean and beautiful picture. That is, user deal with query. Whenever you are writing a query, you don't care what database is trying to do, right? You just enjoy the functionality the database provides that is declarative. On the other hand, we open up the database system, right? And we show you, database tries to do automatic optimization. It's very hard to do, but for many queries, it works. So there's another thing that we need to talk about is in practice, when you are using a database system, sometimes you need to combine these two parts of the world, right? Whenever you are writing a query, sometimes you also need to consider what database is trying to do, because as we can see, the query optimization problem is extremely hard, right? So another thing that we want to talk about is how to close this loop, right? How to take advantage of the insight we have about how database work to really make your query faster. And that is a very interesting topic called tuning, okay? So inside the real world database system, for example, PostgreSQL, there are a lot of those knobs that you can tune, right? So actually for PostgreSQL, I think in 2008, right? So they have like 187 different of those knobs that you can actually tune, you can actually change, right? So here's just some examples, right? The first one is how large the work memory should, you should have, right? So that is actually the memory you are going to use when you're doing, for example, sort merge join, right? How much memory I can use when I do sort merge, right? So, and you can actually specify the cost of random page access, right? You can say, maybe I know beforehand you shouldn't do hash join, it won't go to work. So you can actually disable hash join, and you can have a database system that will not do hash join at all, right? So there's almost 200 of those that you can actually tune, right? We are not going to talk about how to tune them. If you are interested in this, there's a very interesting talk. It's actually 3 hours long about how to tune a PostgreSQL given the query you want to write. So we just want to show you some examples. The goal is when you really go to real world, you have a database, make sure you remember database is something that you often need to tune. Okay, so just remember that, and whenever your query is very slow, think about what could be the potential reason that it is slow, and think about whether you can fix it by tuning. Okay, so and that's the main goal of this. So let's look at some example, right? So let's go back to our hands-on session. It's here. So let's still look at this query. Okay, this is a very simple query. Make this larger. Yeah, it's ugly. It's more beautiful. Okay. Yeah. Okay. So I mean, if you do nothing, this will be search plot. So this is your query plot, right? So you do index like scan on artist, and then you have a sort merge join, right? So once you can do is, for example, you can set your work memory to be extremely large. And then we can actually see what's going to happen. So as you can see, once your work memory is extremely large, right? So the search plan start to change. And the query plan start to change, right? So instead of try to do the sort merge join, right? Now it's actually try to do hash join, right? So which one is better depends on your application, but you can see the different configuration of the database system is going to have a kind of impact on the final query plan. Sometimes as a advanced user of database, you have more information about, maybe it really should do this, maybe it really should do that, right? So, and maybe if the database try to do query in a really suboptimal way, it is entirely possible some of the configurations are not right, okay? So that might be something that you want to consider if your query is very slow in practice, okay? So now let's look at another example, right? So you can, for example, turn off this hash plan, right? Like this hash join. Like for example, you'll say, your work memory is very large, but I know you shouldn't do hash join, right? And magically I know, right? So what you can do is actually, you can tell the query optimizer, okay, whenever you are searching, so whenever you are searching for, sorry, someone called me. Yeah. So sorry. So like whenever you are searching for the query plan, right? So I do not want you to do hash join. Okay. So if you do this, and you do the explain, right? So you can see, right, the database is not trying to do hash join anymore, right? So try to do index scan and then do next loop join, right, for you, right? So, and then you can say, maybe I also do not want to do hash join. Sorry, like maybe I do not want to do sort merge join, right? So you can actually just try to turn off that. And then we can see the optimizer going to, hopefully, yeah. So it's not going to the sort merge anymore, right? It's going to keep doing this next loop, right? So do next loop join, but still going to use index, right? So hypothetically, you feel database shouldn't really do index scan because my random access is so much more expensive than sequential access, right? So as a really advanced user, I have to believe that database is actually using a wrong constant about how expensive random access is, right? So in this case, you can actually adjust the cost model, right? For example, you can actually set the random page access cost to something larger, right? So probably not this large, right? But something larger, reflect the reality, right? And if you do this, and you try to rerun, no, you shouldn't have analyzed this. Yeah. So and then if you redo explain, right? As you can see, after I make the random page like access cost extremely large, right? So the kind of the index scan doesn't really make sense anymore, right? Because I have index, but it's unclassed B tree. I have a lot of random access if I use that, right? So the data is going to actually use sequential scan for you, right? So as you can see, right? So what the optimizer is trying to do is giving all the assumptions on the constant, right? Either the kinetic is estimated or some other constants, right? So like what is the cost of random access, whether you can use hash join, whether you can sort merge join, so on and so forth, and really try its best to give the best plan given those assumptions, right? Whenever you are using a database system, whenever your query is slow, look at the query plan the database try to do and think about whether it makes sense or not. Okay. Sometimes database will give you something that doesn't really make sense because it's a really complex search problem. And as a user, you may have more information that you can use to give the database more guideline about how to navigate this very complex search space. Okay. So we are not going to go really deep into tuning because I mean, yeah, we can spend hours on this. But just to make sure when you are using database for real, for your job, whenever query is slow, remember you could tune it, okay? There's some way that you can actually pass on your domain knowledge, your information, or your insight to the database engine to help it, okay? So that's all we have for today, actually. So we actually finished about how to, essentially how the database system is going to work. So we finished a little bit early today because I want to give you guys some time to if you want, right, finish the teaching evaluation survey, right? So I think everyone just received the email right before the course, right? I think you have 10 or 11 days to finish it, right? So if you want to finish now, we have 15 minutes until the course finish. Yeah, so feel free to do it, right? So I really want you guys to give us feedback by participating in the survey, right? Because so as you can see, that the course is actually, we keep refactor, like improving the course, right? We really want to know from you guys which part of the course you like or which part of the course you do not like, right? So what are the things we should continue to do next year, right? What are things we should stop doing, right? So which equally important, right? How could we run this better? Is there any other material that you want that we provide that could potentially help you to learn, right? Or whatever other feedback, right? So your feedback actually matter to us, and actually it's going to make a difference for next year. Maybe not this year, but for next year, right? For example, if you think about why do we have an exam review session, right? So it's because a couple of years ago, and we don't have that 3 years ago or 4 years ago, right? So because we get feedback from students saying that they want more structures about all the content in the course, right? So we reflect on that. We try to have an exam review session. If you think about why we have the Catacoda thing, right? It's because we get feedback from previous year that students want to take a more active role, right? So we try to facilitate that, right? So we will think about your feedback really carefully and try our best to fix it for next year, right? Maybe not all of them can be reflected this year because we have maybe 3 or 4 weeks, right? So, but it's really going to help us to build a better database course together for next year, right? So yeah, so that's why we finished a little bit early today, right? So if you want to participate in the survey, you can do that in the next 15 minutes, or you want to go back home and you do that back home, right? So just give us feedback. Yeah, so that's all for today. If you have any question, just speak up. Yeah. Otherwise, I will see you guys on Friday. Yeah. Okay, so if no other questions.
Excuse me,
Oh,
I do
yeah,
have a
go ahead.
question.
Sure.
For slide, I think 21.
21. Okay, yeah, go ahead.
It says that projection is can be omitted, but if, for example, projection, if you have a relation R which has A, B, C.
Yeah.
And if your projection 2 is just B and your projection 1 is A. So if you project it to B and then project it to A, you get
but that part is not legal, right?
Which one? Why would it be illegal?
Yeah, for example, like after the first projection, I have a relation with only attribute B, and I want you to project on A. That's not legal, right? I'm asking you to project the attribute, project onto attribute that doesn't really exist.
Ah, okay.
Yeah, makes sense.
Yeah, makes sense. Thank you.
Yeah, perfect. Okay. Yeah, if there's no other questions, yeah, see you guys on Friday.